everyone, this is Netra from AIDS department. I'm going to explain about my mini project. Our mini project title is Polypharmacy Side Effect Risk Predictor, and we are doing this by using quantum machine learning. So, like our aim is to predict the risk levels when we intake multiple drugs at the same time. It is a drug-drug interaction which pose serious risk in polypharmacy, leading to adverse reactions and increased healthcare burden. So we are using like quantum machine learning in this project, but in traditional methods, we rely on clinical trials and rule-based systems which cannot scale to the enormous combination space of modern drug databases. So our project applies hybrid classical machine learning to predict interaction risk levels between drug pairs using molecular fingerprints and variational quantum circuits. The adverse drug reactions caused by drug-drug interaction remain a major clinical challenge. The classical machine learning struggles with extremely high-dimensional molecular data and non-linear biochemical relationships. Manual evaluation of drug risk is slow, error-prone, and not scalable. Our objective of the project is to design a hybrid quantum model capable of predicting low, moderate, or high interaction risk for SMILES encoded drug pairs. Our scope of the project is drug-drug interaction risk prediction. We focus on developing a hybrid quantum classical machine learning model for predicting interaction risk between drug pairs. We utilize molecular fingerprints, which is Morgan fingerprints, and PCA compression and variational quantum classifier for risk prediction. Our targeted audience is medical professionals, pharmacologists, healthcare researchers, and clinical decision support teams. A fully trained and like what we deliver is a fully trained and evaluated hybrid QML model for predicting low, moderate, high interaction risk. A user-friendly interface for model deployment and documentation describing data processing, model architecture, training pipeline, evaluation metrics, and deployment workflow. We use Kaggle for data set, and we convert the drug names into smiles, and then we will convert the smiles into Morgan fingerprints. We are using PCA to reduce the dimensions, and we are training the baseline classical models and hybrid QML model, and we are building a prediction interface for risk scoring. And like about our data set, we are using a publicly available Kaggle data set containing drug pairs and associated side effects. We convert drug names into smiles using PubChem and generate Morgan fingerprints and apply pre-processing steps such as cleaning, label encoding, and dimensionality reduction. Yeah, we have some limitations, which is data quality and bias. The interaction data may not fully represent all clinically known drug combinations and feature representation constraints. Morgan fingerprints and PCA compressed vectors may lose certain chemical or pharmacological details. And third limitation is quantum hardware constraints. Current quantum circuits are trained on simulators. Real hardware is limited by noise and qubit count. Dataset acquisition is drug pairs and side effect labels were collected from Kaggle and prepared for supervised learning. And data pre-processing, data names were converted to smiles, Morgan fingerprints were generated, labels encoded, and PC applied to reduce the 2048 dimensional vectors into quantum compatible features. Then hybrid quantum model development. A variation quantum classical model was built using angle embedding and strongly entangling layers, followed by a classical linear head for risk classification. And then we are developing a web app. A user-friendly interface was created to accept drug inputs and display interaction risk predictions generated by the trained model. And last one is integration and testing. The hybrid model was integrated with the web app and evaluated against classical baselines to ensure accuracy, reliability, and consistent performance. Our hybrid quantum machine learning model includes designing a classical feature encoder and encoding features into quantum circuits using angle embedding and applying strongly entangling layers for variational learning. Training the hybrid quantum classical model via backpropagation, so benchmarking performance against a random forest baseline and evaluating results using accuracy and F1 score metrics. So this is how our system works. This is the architecture diagram of our project. So first we are collecting the data set from the Kaggle, and then we are extracting the features. Then we are inputting the features into quantum encoding for encoding like molecular fingerprints, and then we are feeding that molecular fingerprints into hybrid QML model. So it then predicts the risk level as low, moderate, or high, and then it will deliver to the user. So this is how our project works. Yeah. What are the algorithms we are used here is Morgan fingerprint algorithm, which is used to convert drug molecular structures represented as smiles into fixed length numerical feature vectors, and it captures structural and topological information of molecules using circular substructure hashing, and it enables effective representation of chemical properties required for interaction prediction, and it fingerprints of two drugs or concatenated to model pairwise interactions. The next algorithm we are using here is PCA, which is principal component analysis. It is used to reduce the high dimensional fingerprint vectors into low dimensional representations. It preserves maximum variance while making the data compatible with quantum circuit constraints, and it improves chaining efficiency and reduces computational complexity. And also we are using VQC, which is variational quantum classifier. It is a hybrid quantum classical algorithm implemented using penny uses angle embedding to encode classical features into quantum states. So, strongly entangling layers from a parameterized quantum circuit for learning complex patterns. So, quantum expectation values are used as features for final risk classification. And also, we are using random forest classifier. It is a baseline model. So, it is a classical ensemble learning algorithm used for benchmarking, and it trains multiple decision trees to improve robustness and reduce overfitting. It serves as a performance baseline to evaluate the effectiveness of the quantum enhanced model. So, what are the software we are using here is Pennyline, which is a hybrid quantum classical model development, and we are using PyTorch used for classical encoder optimization and training pipeline, and then we are using Scikit-learn. Which is used for PCA, random forest baseline, and evaluation metrics, and then NumPy and Pandas, which is used for data preprocessing and storage. So the hardware is the what are the hardware we need is Python, Jupyter Notebook, and VS Code, and GitHub. So let us see how our implemented the project. So this is how we implemented our project. So first we imported the necessary libraries we are required for the project, and then we converted the features into qubits. Like as we are using quantum machine learning, so we are just converting the features into qubits for further processing. Then we are defining a quantum circuit here. So we are using angle embedding and strong entangling layers for the further process. And then we are defining a hybrid model. So for encoding the features, and then here we are defining the forward function. Then we are using like by using train to split we are splitting the dataset into training dataset and testing dataset, and then we are applying the loss function to the model, and then the training starts here by defining the epochs, and then we are also predicting the accuracy score and F1 score. I have saved this model to a separate path like called hybrid model encoder path, so the model will save to that path. Yeah, so this is our accuracy result. we are getting 34.12 percentage as accuracy, though it is a very less accurate, but when implementing in quantum hardware, it will result better. Like, as of now, the hardware is still developing, we are getting this much accuracy, but when we develop the hardware, the result will be high and more accurate. So this is how our epoch will run and the accuracy will show. Let us see the demo of our project. So this is how our project work. So this is this demo work. First, I'm taking the aspirin as drug 1 name and atorvastatin as drug 2 name. So let us fetch the smiles. Yeah, you can see here the smiles are fetched using PubChem. Next, let us predict the risk level. Yeah, the model predicts this as a low risk. So when we intake these two drugs simultaneously, it will not lead to that much side effect. So you can intake these two drugs simultaneously. So this is how our model works and predicts the side effect risk. So in this project, so I conclude that we explored a hybrid quantum classical approach for predicting drug-drug interaction risk using molecular fingerprints and variation quantum circuits. The experimental results show that the proposed model achieves performance comparable to a classical baseline, demonstrating the feasibility of applying quantum machine learning techniques to pharmacological risk prediction under current simulation constraints. Our future work is in the current work, the model is limited to pairwise drug interactions and simulator based quantum execution. In the future, we plan to explore deeper quantum circuits, alternative embedding strategies, and execution on real quantum hardware. So, further improvements include extending the framework to multi drug interactions, incorporating richer pharmacological features, and benchmarking against stronger classical models to enhance predictive performance and robustness. So yeah, we have given our GitHub project link also. I can verify that. Thank you.